Okay, so once again you are most welcome. My name is Mtanda Samir. Now this time round, please, we are now back on our physics revision series. This time round, we are in for item 16, or which you can call item 016 in simple terms. That's where we are. Now this is specifically coming from a subtopic measurements. All right, good. And now please, we are going to look at some good interesting things here. My humble request to you is that watch the video to the end, especially if you're a teacher or if you're a senior post student. Better watch to the end. And of course, I call you to at least keep on to the playlists. You check in the playlists. We have math, we have physics and chemistry right on this channel. So you consider watching. You never know, you may land on an item part of what you have watched right here. So the more you watch, the more you increase your chances. Of course, just a paper only has math has only 6 items, and of course we have more than 30 items uploaded here in math, more than 30 uploaded for physics, more than 30 uploaded for chemistry. Okay, that's a good way to go, I guess. All right, now let's start off without wasting time, but please remember to subscribe to the channel. All right, good, let's go there. Okay, still remind you to subscribe to the channel, like, share and comment right away. So we call you to share, like and comment. Right, now without wasting time, let's get to the question straight away. Okay, so we shall follow up a little bit. So they're saying a certain family uses a special type of wax candle for multiple purposes. Oh, anyway, they use candles anyway, including mosquito repellents. Now mosquito repellents, those are, I don't know whether how I can explain this is that, but it is more like a small, okay, you have all ever seen a perfume bottle, one with in fact a perfume bottle glass, like one with a clear glass whereby you can easily see the tube which carries the perfume from the bottle on the outside. So that's how a perfume repellent is, rather a mosquito repellent is. Now the others which are electric, it has some liquid somewhere, but you connect the power source, whereby I think that power source has the way it heats up this rather the mosquito repellent, and it will spread away like the way you see the perfume. Anyway, sources of mosquito repellent, sources of light and heat and timer. This type of candle has the uniform cross-section area of 3.0 centimeters squared, length of 15.0 centimeters, and a mass of 39.0 grams. As it burns, wax melts at a rate of 2 centimeters per 30 minutes. Great. It generates an odor. Odor is more like a smell, which repels mosquitoes in all rooms in the house. A student in the house is planning to use a similar candle of length 10.0 centimeters to revise at night from 8 p.m. to 11 p.m. Alright, he is not sure whether this will be possible. The family also intends to place this type of candle on the water in a small water pool in order to chase the mosquito. Okay, in bracket, density, where I need B, density of water is same as 1 gram per centimeters cubed. As a student of physics part A, help this family to understand how the mosquito are chased away from all rooms, including the ceiling. How are the mosquito chased away? Part B, advise the family on whether the candle will be able to float on water. Oh, there is need for some space here, spacing those words on and the water. Okay, lastly, part C, the saying, help the student find out. Alright, help the student find out whether the candle will burn for his planned time. Part D, suggest other traditional ways of measuring time. Anyway, other traditional ways of measuring time, shall get onto that. So okay, I think let's go back. Let's go back and refer to the question. So part A is saying, help this family to understand how mosquitoes are chased away from all rooms, including the ceiling. Now what you must know here is that we have this. Just imagine this is a room, and maybe, okay, an experiment here I can bring is that, just imagine if we have, say for example, a rotten egg. We have a rotten egg around here. This one here is a rotten, it is a rotten egg, and it is broken right from here. Wow, now you find that even someone this side in the other corner will be able to get the smell of the rotten egg to that. Now the process by which the smell moves from the egg itself to the person, that process there we call it what? That process there we simply call it diffusion. I know you all know this. We simply call it diffusion. Or in simple terms, just imagine there is a burning heat source somewhere, and for you at this side, like this. Now, how does that smoke move to reach you? That smoke moves basing on the process of what we call what? Diffusion. We have very many experiments, okay, which prove this. However, that's not the topic of today. Now, we are going to just look at diffusion as a term. Now, in diffusion, there is this term here. We have what we call a high concentration, and then we have what we call low concentration. Let's pay attention to these two terminologies here. You have what we call a high concentration and low concentration. Now, if you're talking about, let's talk about this. Maybe, okay, let's just compare this. A toilet. Now, a toilet, no, okay, maybe a toilet may not be a friendly to some people. I will again use a rotten egg, I think so. Let's use a rotten egg again. Toilet may not be friendly to some people, of course we mentioned that. Now let's go to a rotten egg. Now, if this is our rotten egg, this one here is our rotten egg, and you individual, the person who is getting the smell here, you're right here. Now, if you realize that the smell is moving from here up to this side. Now, where the smell is coming from is a region of high concentration, and where the smell is going is a region of low concentration. So the high concentration is the source of origin, where the smell is starting from, and lower concentration is where the smell is going. So this gives us a definition of what diffusion is. Diffusion is the movement of particles from a region of higher concentration to a region of lower concentration, in simple terms. And now that part A is answered based on that we can have our mosquito repellent right here. It's more like a bottle, by the way, if you didn't know. Like this, more like a bottle but having some liquids in there. Sometimes they even connect it to power source, just like you have that charger which charges your phone. It is connected in here, then you place it into the socket. When you enter that into a socket like that, this thing, it will receive current, and now the current will make this to evaporate to produce some vapor. Now that vapor there will move out here and saturate all through the room. Now if this is our room like this, and the repellent is right here, and the mosquitoes are this side, this is the mosquito. From a repellent to the mosquito there, it moves as a process of diffusion. Okay, but of course, just the repellent is heated, it makes a vapor, the vapor moves from the repellent to the mosquito. Repellent, higher concentration, mosquito, low concentration. Let's go there and see that. So you're getting part A answered. Let's go there. Okay, let's get part A answered. So you're saying, part A is saying that when the wax is burnt, it produces vapor. The molecules of vapor, in bracket fumes, move from a point of high concentration to a region of lower concentration, spreading through all rooms by diffusion. The warm fumes rise up to the ceiling. The vapor fumes are able to chase away the mosquitoes. Now, I think let's get this explained slow but sure. Okay, now, so you say that the wax is burnt. Yeah, what happens? Once it's burnt, it produces the vapor. I explained that. Now, that vapor is then you're talking about. The vapor is going, but of course, remember the other point of region of higher concentration and region of low concentration. Let's go there. So, the molecules of the vapor, you can even call of this. You can just call you can call the fumes. The molecules of the vapor move from a point of higher concentration. That's where the repellent is. Where the repellent is to a region of lower concentration. That's where now the mosquito is. I've explained that. Spreading through all the room, but all the rooms by diffusion. Of course, I explained what diffusion is. Okay, the warm fume rises up to the ceiling. Okay, raises up the ceiling. Now you all know that in physics, when something is hot and something is cold, we take it that something which is cold is a bit heavy, and something which is hot is a bit light. That's what we take it in physics. So, of course, you know that when you are arranging things, you find that the heavy one will be down, heavy, and the light one will be up. light. So here the fumes, since the fumes are already hot, they will move. If this is the room, find that the cold air will go down and the hot fumes will go up. That's how the cycle goes, and we get that explained. In fact, in simple terms, that's how it comes about. It begins by heating the wax. What does it? Produces the vapor. What happens to the vapor? The vapor now moves from a region of high concentration to a region of lower concentration. That is simply by diffusion. How? Now, the warm fume rises up the ceiling. Alright, good. Now, the vapor or fumes are able to chase away the mosquitoes in simple terms. Okay. Now, hope that is real. That really makes some bit of sense. Let's still continue. Now, still let's fall back to our question. The thing, part B. Advise, alright, let's get this done. So, advise the family, there's a pen. Advise the family on whether the candle will be able to float on water. Now, what you must know is that from the law of flotation, realize that for anything to float, we base on its what? Its density. By the way, for anything to float, we base on its density. And you all know from definition, density is the mass per unit volume. Now, for anything to float, like say for example, if this is a tin, like this, remember the density of water is 1 gram. I've given it to you here. The density of water is 1 gram centimeters cubed. Now it means that this water something can float if it has a density less than that of water. If the density is less than that of water, it will float. Like say for example, if the density is less than this, then it will do what? It will float. Then if the density is greater than this density of water, then the substance will sink. Now what does it mean? It means that here we must go ahead and calculate the density of the candle. And after calculating the density of the candle, we shall compare it with the density of the water, which is where we are going to put the candle for it to float or sink. After that, then we shall be able to get the value. And once you get the value of the density, we shall compare. But of course, I've given you the grounds on which you will know whether to float or to sink. Okay, now let's go and pick the information about density. Now what you must know is that density is equal to mass over volume. Now just to ask, do you have the volume? Do you have the mass? Yes. Where is the mass? The mass is right here, like we are. So the mass, we have it as that 390. Now we shall leave the grams as grams because even this density has grams in it, so we shall not need to convert to kilograms. Now the volume, but do we have the volume? Okay, unlucky. Now about this, we have the dimensions: area of 3 centimeters squared and length of this. Now we all know that volume, in simple terms, this volume here is the same as the area times length. Sometimes the volume can be gotten as that. Now once you calculate the area times the length, you give us the volume, we divide and then compare. We shall be able to get the density and compare with the density of water and know whether it will float. So for example, we shall say, okay, alright, so area is equal to 3 centimeters squared. We are noting from the question. Next, the length is equal to 15 centimeters and mass is equal to 39. Now 39, please, what you should know is that 39.0, there's a point here, 39, okay, this is 9, 39 point, okay, 39 grams point 0 is just the same as 39 grams, like that. That point 0, you may not necessarily bring it forward in the calculations. It's just a level of accuracy. Okay, they're trying to show in the question. So you have length is that, but we all know that volume, please, volume is equal to the area times length. How? By the way, how? You can take it from the volume of a cylinder. I will give an example. Volume of a cylinder is equal to pi r squared h. Now volume is equal to, but are you aware that pi r squared alone is the area of a circle? Do you see that? Is the area of a circle. So this one I'll call it area, is area, but times the height. But the height is a length. So that's why we always say that in physics. That's why in physics we say that volume is equal to the area times the length. So let's get that. We have the area as this, we have the length as this. we can now calculate our volume so that we can get our density. So volume is equal to area times length. So by substitution, we shall have a 3, which is our area here, times the 15, which is the length right there. But remember, the SI unit is centimeters cubed, so we shall get 45 cubic centimeters. Hope that will make some bit of alright sense. Okay, now with that, let's now proceed. But we all know that volume is equal to, in fact not volume but density. Surely this is meant to be density. Sorry, this is meant to be density by the way. Density is equal to that. So therefore, okay, density is equal to mass over volume. So finally, please upside this one, take it to be density. I'm really sorry for that. So again, when you now, but remember, our mass was 39 and our volume was 45 from right here, and our mass from right here, right there. Okay, good. Now let's substitute. Please, we have the density. That's a density, not volume necessarily, because in here we wanted to find the density in simple terms. Get this erased. Then the answer will be 0.8667 cubic centimeters, rather grams per cubic centimeters. That is density, please. That is density. That really makes some sense. So now the density, look at this density here. Comparing to the density of water. Remember, density of water was 1 gram per centimeters cubed. Then I want to ask, will it float? Will it float? Now I say that if the density is less, now this density here is less, it means that it will float. I would explain that. So let's conclude and say, since the density of water was less than that, since the density of the wax was less than that of water, of course reminding you the one of water was 1 gram per centimeters cubed, then the candle will float on water. As simple as that. And now that explains why the candle will float. An object with a density which is greater than that of water, it will to automatically sink. Like yourself, once you're going to fall in water, you automatically sink because your density is by far greater than that one of right water. Okay, now let's can see part B. Is it part C? Okay, part C the same. Okay. Now think, help the student to find out whether the candle will burn for his planned time. Oh, now about planned time, let's go back in the question and see. About this planned time, let's go back in the question and see. About the planned time, let's go back in the question and see. Now think, a student in this house is planning to use a similar candle of length 10 centimeters to revise at night from 8 p.m. to 11 p.m. He is not sure whether this will be possible. Okay, anyway, the family also intends to place a type of a candle in water. Anyway, now we want to see, will it be possible for him to use this kind of candle? Anyway, but I've told us somewhere here that as it burns, wax melts at a rate of 2 centimeters per 30 minutes. So every 30 minutes it melts by 2 centimeters. Now they're asking, if he has a candle which is 10 centimeters long, will it be enough to revise from 8 p.m. to 11 p.m? Let's go back there and see how that can be answered. Let's go there. Okay, so let's see. We start off. So let's remind you that candle melts at a rate of 2 centimeters per 30 minutes. That's what we know about that. Then also what you must know is that from 11 p.m. to 8 p.m, that is equivalent to a duration of 3 hours. If you try to get this calculated, please. From 11, we have 11. Okay, from 11 I have 11. I have 11. From there we have 12. From there we have 7. From there we have what call what? 8. But the counting is the counting is, let me use a different ink. The counting is like this: 1, 2, 3. So that's the 3 hours. 1, 2, 3. Are you able to see that there are 3 hours between 11 p.m. to 8 p.m? There are 3 good hours there. So we need to know that how long does it take. So the boy wants to read it from here up to this, and those are 3 good hours. But remember, every 2 centimeters, a candle, every 30 minutes, a candle melts 2 centimeters. Anyway, we don't know if that will be enough. as we are calculating, we are as well praying for him. Maybe the candle will be enough. Anyway, I guess it's in a countryside where we don't have electricity. Okay, so 30 minutes. Now let's first of all convert the 30 minutes. Remember, this one is in hours, so let's get this 30 minutes here into what? Into hours first. So 30 minutes, convert them into hours. How shall we get there? We simply divide by 60. So when you divide the 30 by 60, it will give you 0.5 hours. Now that implies that every 2 centimeters it takes 0.5 hours. Now we must see the 3 hours this boy wants to read. We'll take which length of the candle. Remember, the candle he has at hand is of 10 centimeters. If we get once we get the length which is greater than what the candle he has, then it will be a no, will not be enough. But if the length is less than what he has, then it will be a yes. He will be in a position to at least be able to read. And our humble prayer is that maybe it may be enough for him. Okay, now we have the length there. Okay, we have everything there. Okay, now I've put here, remember this one here is a length right there, and this one here is the minutes, that is time. So I'm beginning with the first statement. 2 centimeters of length takes how long? Takes 0.5. That's very good. But again, from 11 to 8 takes 3 hours. So what about if 0.5 hours consume 2 centimeters of the candle? What about the 3 hours will consume how many of the candle? I put letter X there to mean that. So you write them in fraction form like that. Letters of this. So again, you simply put this here, a bar and an equal sign, a bar. Then you equate, just like we have here, a 2 over x. We have here a 2 over x. This one is an equal sign, a 0.5 over 3, a 0.5 over 3. We calculate and get the value of x. Now we want to see if 0.5 hours take 2 centimeters of the candle, what about 3 hours of which this boy wants to read? Which length will be required? That length shall compare it with the 12 centimeters of the candle available, and we see whether it will be enough. And we have said our prayer is, we are praying that it may be enough for him. Okay, by cross multiplying, you realize that, I think let's get this here. Okay, so by cross multiplying, you realize that when you cross multiply, okay, get this there. Okay, there's been some technical error, but no problem. So multiply this by this, you'll get 0.5x. 2 times 3 will give you a 6. Okay, dividing both sides, 0.5 will cancel with 0.5. 6 divided by 0.5, you get a 12. Please use a calculator here. It gives you 12 centimeters. And this boy is lucky. Remember, the candle is of 10 centimeters, but is unlucky by the way. The candle has is of 10 centimeters, yet the 3 hours he wants to read take 12 centimeters of the candle. Okay, sorry. So we said the boy has 10 centimeters length of the candle, yet he needs 12.0 centimeter length of the candle. So the candle will not be able to reach 11 p.m. Not even 11 p.m. but to reach 8:00 p.m. Simple terms. Anyway, sorry for him. And I know, of course, when the candle has not been enough, guess what happens? This person will be like this, will be like that, very annoyed. Anyway, sorry for him, candle was not enough. Okay, now that marks the end of this question. However, still I'll comment on this. Please, I'm not bothered to write about this, but I'll just brainstorm. Okay, traditional ways of measuring time, okay. Alright, now, okay, I want to get this answered right here. Now, the different other traditional ways how we can measure time is that, okay, now we can use what we call a sand timer. You all know what a sand timer is. Let me just write some, okay. We have what we call a sandy. A sandy timer. Now a sand timer, you've ever seen it in movies. It's more like this. It's made in this format here like this. like this, whereby it will have sand up here, then that sand will keep pouring gradually downwards. That's what we call the sandy timer. Now another traditional way of, apart from, of course, nowadays traditional means the ones they used to use in back then. Now in the present day we use, in fact in the present day we use the digital watches, the clocks, but here they used not use that. So next, apart from that, in fact, we can also talk about the sundials. We have what called a sundial. A sundial, this is I, this is S-U-N-D-I-L. Sundials, this is L. Now sundials, this one here is by telling the position of the sun. Maybe if someone is standing right here, like this, maybe this is the ground, and this one is shadow is portraying in that direction. This one is shadow is portraying in that direction, and this one is shadow is very short. People used to tell time using that. That is, we have sun timer and the sundials. Sundials means the time, how the time moves. Now next also we have what we call candle clocks. Candle clocks. Please, I'm hinting on this. Candle clocks. Now candle clocks, what they use? They used to put markings on a candle. Like, say for example, we have this. Then they put markings like that. Now maybe they'll be like, maybe someone is going to run, maybe people are going to run, or someone has gone somewhere. They'll use these markings here to say, okay, now it has taken you 3 markings to do the work. You are very slow, but another person takes only 1 mark of the candle melting to do the work. So we call that candle clocks. This is K, candle clocks. Then also next, we also have what we call a water clock. Water clock. Now water clock, here they used to use that how long does water take to dry. Like, for example, they can pour water on the surface, then they tell you, okay, you can now go. The time the water takes to dry will be used to tell how long. The more the water stays, the more they can be able to tell how long you have taken, as far as that is concerned. Okay, now we have not had it clearly here, but I hope that really makes some sense. That's some of the traditional ways of measuring time. Now we have sand timer, we have sundials, we have candle clocks, and we have water. There are many more, but those ones are enough as far as our video is concerned. Okay, now I wish you well. Let's end there. I think more to come.